What if a bookbinder's apprentice could unlock the invisible forces that bind the universe? In a single night of candlelit study, he wrote a letter that would change the course of science forever. In the sooty-stained streets of Newington Butts, a boy named Michael Faraday entered the world on the 22nd of September, 1791, the son of a blacksmith who could barely afford bread. By the age of 13 he was apprenticed to a bookbinder, a trade that gave him unrestricted access to the pages of the Encyclopedia Britannica and the latest scientific journals. He devoured every article on chemistry and electricity, copying diagrams into his own notebooks by candlelight. The young apprentice taught himself the rudiments of Latin and French to read foreign papers, a rare feat for a working-class youth. In 1810 a chance encounter with a lecture by the charismatic Humphry Davy at the Royal Institution ignited a fire that would never be extinguished. Faraday scribbled a heartfelt letter to Davy, enclosing his own notes on the decomposition of salts, and begged for a position. Davy, impressed by the clarity of the boy's mind, offered him a ticket to the next series of lectures. That ticket became the passport that carried Faraday from the bindery bench into the laboratory of the Newington leading chemist. The moment marked the first turning point in a life that would rewrite the language of nature. Faraday entered the Royal Institution in 1813 as Davy's laboratory assistant, a role that placed him beside bubbling retorts, voltaic piles, and the sharp scent of chlorine. He learned to prepare the delicate apparatus for Davy's public demonstrations, mastering the art of precise measurement and meticulous record-keeping. The young assistant accompanied Davy on a continental tour, meeting Andra copyright symbol A Marie Ampère in Paris and witnessing the first electromagnet in action. These encounters planted the seed of a revolutionary idea, that electricity and magnetism were not separate curiosities but manifestations of a single force. Back in London, Faraday began his own systematic investigations, publishing his first paper on the analysis of native copper in 1820. His reputation grew, and in 1821 he was appointed superintendent of the house and laboratory, a position that granted him a modest salary and a private workspace. The institution became his sanctuary, a place where the hum of batteries and the glow of gas lamps formed the backdrop to his relentless curiosity. In 1821 Faraday achieved a feat that would astonish the scientific world. He built the first device to convert electrical energy into continuous mechanical motion. Using a mercury bath, a vertical wire, and a permanent magnet, he demonstrated that a current-carrying conductor experiences a force perpendicular to both the current direction and the magnetic field. The wire rotated around the magnet, a simple yet profound proof that electricity could produce motion without any chemical reaction. He published the results in the Quarterly Journal of Science, describing the experiment with characteristic clarity and providing a sketch that would become the textbook illustration of electromagnetic rotation. The discovery laid the groundwork for the electric motor, an invention that would later power factories, trains, and the very fabric of modern industry. Faraday's motor was not a commercial product but a proof of principle, a beacon that guided future engineers like William Sturgeon and Thomas Davenport. Faraday's law of electromagnetic induction, the induced electromotive force equals the negative rate of change of magnetic flux. Parallel to his magnetic researches, Faraday turned his quantitative eye to the chemical effects of electricity, formulating the two laws of electrolysis in 1833. The first law states that the mass of a substance liberated at an electrode is directly proportional to the quantity of electricity passed through the electrolyte. The second law reveals that the masses of different substances liberated by the same quantity of electricity are proportional to their chemical equivalent weights. He measured the charge using a calibrated voltaic pile and a silver coulometer, achieving unprecedented precision. These laws provided the first reliable bridge between chemical affinity and electrical charge, enabling the later definition of the Faraday constant A the charge per mole of electrons. Faraday-S meticulous tables of electrochemical equivalents became the standard reference for chemists and the emerging field of electroplating. Faraday's first law of electrolysis, mass liberated is proportional to the charge passed, with m molar mass, n valence, F Faraday constant. By the 1840s, Faraday-S relentless laboratory work began to exact a toll on his health. He suffered from chronic headaches, memory lapses, and a trembling hand that made delicate manipulations difficult. Despite these afflictions, he was elected a Fellow of the Royal Society in 1824, awarded the Royal Medal in 1835 and 1846, and offered the presidency of the Society in 1857, which he declined, preferring the quiet of research. Queen Victoria granted him a Gratia and a Favour House at Hampton Court in 1848, a rare honour for a man of his origins. He continued to advise the government on lighthouse illumination, the protection of ships' hulls from corrosion, and the standardization of electrical units. His practical mindset ensured that his discoveries never remained abstract. They illuminated coastlines, powered telegraph lines, and safeguarded the Navy. When James Clerk Maxwell published his treatise on electricity and magnetism in 1873, he explicitly credited Faraday-S experimental philosophy as the foundation of his mathematical framework. Maxwell translated Faraday-S lines of force into the differential form of the equations that now bear his name, embedding the concept of a dynamic electromagnetic field into the language of calculus. The four Maxwell equations Gauss-S law for electricity, Gauss-S law for magnetism, Faraday-S law of induction, and Ampere-Maxwell law encapsulate the unity Faraday had sensed decades earlier. Faraday-S law appears as the curl of the electric field equals the negative time derivative of the magnetic field, a direct mathematical echo of his 1831 discovery. This synthesis enabled Heinrich Hertz to generate and detect electromagnetic waves in 1887, opening the door to radio, radar, and the entire wireless world. Maxwell-Faraday equation: a changing magnetic field creates a circulating electric field, the mathematical form of Faraday's induction law. Faraday spent his last decade in the tranquil surroundings of Hampton Court, surrounded by the gardens he loved and the notebooks that chronicled a lifetime of wonder. He continued to correspond with younger scientists, offering gentle guidance to the likes of John Tyndall and William Crookes, while refusing to engage in the fierce priority disputes that plagued the scientific community. His memory faded, but his curiosity never dimmed. He would still ask visitors to describe the latest telegraph line or the new electric light. On the 25th of August, 1867, at the age of 75, Michael Faraday passed away peacefully in his sleep. The Royal Institution draped its lecture hall in black, and the scientific world mourned the loss of a man who had turned the invisible into the indispensable. But as Michael Faraday's candle dimmed in 1867, a child was born in 1809 who would turn the living world into a laboratory of change. Charles Darwin's voyage was about to begin, and the echoes of Faraday's fields would whisper through the theory of natural selection. Subscribe, and don't miss it.